Okay, we started our recording. So welcome to the Montana Tech Public Lecture Series. Today is one of the two Earth Science and Engineering hosted public lecture series speakers. And so today we are very happy to have Dr. Thomas Oommen with us. And especially happy because he's missing his daughter's basketball championship game. So we are very thankful that he decided to give this talk to us today. And so Dr. Oommen is in the Department of Geological and Mining Engineering and Sciences and an affiliate professor in the Department of Civil and Environmental Engineering at Michigan Tech. So we have a lot of connections with tech here at Montana Tech. He's the director of the Computational Science and Engineering Interdisciplinary PhD program, and his research focuses on developing improved susceptibility characterization and documentation of geohazards, on developing improved georesources over a range of spatial scales and data types. And so to do all this, he has adopted an interdisciplinary research approach from two main areas, aerial satellite-based remote sensing for obtaining data and artificial intelligence, machine learning for data processing and modeling. And his PhD is in civil and environmental engineering with emphasis in geotechnical engineering from Tufts University. And his master's is in systems engineering from University of Alaska Fairbanks, and a BE degree in civil engineering from Bangalore University. So thank you very much for agreeing to speak with us today. We're very pleased to hear what you have to say. Thank you.
Thank you. Thank you, Professor Cox, for the introduction, and thank you for inviting me to this Montana Tech public lecture series. And I'm glad for this opportunity. I hope you are able to see my screen very well and hear me well.
That's good.
Okay, my dog is barking in the background, but hopefully it will stop now. So the title of my presentation is A New Paradigm in Geotechnical Performance Monitoring Using Remote Sensing. And I will actually, as I walk you through this presentation, I'll show you why we need a new paradigm and how the remote sensing can make a big change in the way we do things currently. So here in this slide, let me actually show you the significance of the work that we are doing. So you can see in this slide that on the left top corner, what you see is the map of the levees in US. And on the right top corner, what you have is the road network. The black lines represent the road network. The one with the red color, it shows the landslide hazard map for US developed by the US Geological Survey. Now, with the overlay of the landslides hazard map on the road network, you can actually see that there is a huge or there is a large number of road network that is vulnerable to landslides in US. If you overlay that same landslide susceptibility on the map of levees or the map of 8,100 major dams in the United States, you would actually see that many of these critical infrastructure is vulnerable to landslides and ground movement in US. Now, in addition to this, when we consider the aging infrastructure that we have and the uncertainty over climate change with increase in extreme rainfall, to build and forget is not an option for us engineers. The traditional approach was to build it and we forget it. We do some regular maintenance, but we don't monitor these critical assets for some of these hazards. With this high landslide potential and with the aging infrastructure, that is not an option anymore. And I would actually show you more examples why that is true. So Traditionally, we do performance monitoring of infrastructure to characterize the site prior to a design or monitor construction activities, monitor performance of a structure, compare design assumptions to actual loading conditions, identify problems they lead to failure. So these are the traditional reasons for doing monitoring. And now, how do we do monitoring of landslides and critical infrastructure? So the traditional approach to do that is using inclinometer or tilt meter for lateral deformation, or to use rod extensometer, settlement cells, or horizontal inclinometers for vertical deformation. So these are point measurements. So at a point, you do get the measurement from these approaches. Now, these point measurements are pretty accurate. They're very useful. Um, and here is an example. This is an example of a slope that is being monitored with extensive ground instrumentation. You can actually see here there were about 12 of these sensors put, and there were both rain gauges and extensometers, and it was monitoring for the rainfall and the tilt angle. And as the tilting of the slope occurred, you can see as the tilting increases, it led to the slope failure. So before the slope failure, you can actually detect where that slope is tilting, and you have an early warning system um, to reduce the risk that the slope failure could cause, particularly say if it is near a dam or a road network. You can actually stop the traffic, or say if you can evacuate people from downstream areas of the dam. So you can actually reduce the risk if you have accurate early warning. But the challenge that we are facing the with this large network of areas that is vulnerable to landslides, putting these instrumentations everywhere and analyzing and making sure these instruments are working correctly and getting that data is almost impossible. So the traditional approach is pretty accurate. It works very well. We can utilize it for an area where there is where we know that it is vulnerable. But when you have large areas to monitor, the traditional approach of using these slope tilt sensors or in situ measurements are challenging or almost impossible. So that is where I make that case that we do need a new paradigm using remote sensing for performance monitoring in geotechnical engineering, considering the uncertainties that we face. Now, what is remote sensing? Remote sensing is making measurements remotely without being in contact. Traditionally, remote sensing is done using the electromagnetic radiations, and there are several different remote sensing techniques. Insar, which is called interferometric synthetic aperture radar, LiDAR, light deflection and radiometry, photogrammetry, thermal imaging, multispectral imaging, hyperspectral imaging. And these remote sensing can be done from different platforms, can be done from satellite platforms, aerial platforms, and even terrestrial platforms like stationary or mobile. So there are different options in terms of these remote sensing techniques, different platforms. In this presentation, I would actually highlight to you some examples of INSAR, photogrammetry, and thermal from different platforms, from satellite, aerial platforms. and how these techniques are being used for different performance monitoring applications. So I would like to actually present a series of case studies where I can actually show you how these techniques can be used for performance monitoring as to complement the traditional approach or even to substitute the traditional approach in some cases. So let me begin with Insar, how Insar can be used. And I don't want to go into too much of the theory of Insar, but I still want to give you some basic understanding. Insar is based on the SAR remote sensing technique, where SAR stands for synthetic aperture radar. And it works by illuminating the Earth with a beam of coherent microwave radiation, which is similar to a laser. And when that radiation is touches the Earth and it returns, you get actually two measurements. You get an amplitude and you get a phase. And the phase of a radar can be utilized to make accurate distance measurements or change in distance. Now, there are different um, wavelengths of these radiations. And if you look at the SAR literature, you would see that there is X-band satellites, C-band satellites, and L-band. Now, within these different bands, one thing that I want to point out that is quite important when you're starting to use INSAR in any of your research or in your work is that the maximum displacement that you can measure using a radar SAR or INSAR approach is half the wavelength. So that this is very, very important because with radar, you cannot actually measure large deformations. You can only measure small deformations. So for example, if you're using an X-band satellite, the maximum deformation that you can measure is 1.5 centimeter between two satellite passes. So between those two satellite passes, if your location is moving more than that, you will not be able to detect. So this is also a limitation of the radar. But when we look at the geotechnical applications, this is not a huge limitation. This is really something um, uh, not a huge issue. And the reason is when there is large displacements, we sometimes don't need radar or satellite-based measurements. Those displacements are clearly observed on the ground. So small movements are the ones that we don't notice so clearly. And that is where we really need these monitoring techniques. So um, the INSAR works really well. So now let me show you a schematic that would actually walk you, or this would walk you through how that SAR technology works. So say you have a first acquisition being done with a satellite or time one, and then a second acquisition happens at time two. And between the time one and time two, the location that you're monitoring had some ground movement, and that ground movement can be detected as the change in the range. And that is where the INSAR approach is quite valuable. Now, uh, the beauty of INSAR is that these satellites are measuring from about 800 kilometers from the Earth, but their wavelengths are in centimeter scale. So because you are using the wavelength to measure the change in phase, and because the wavelengths are in centimeter scale, you can actually make very precise measurements, millimeter scale ground movements using these INSAR approach. So with that background, let me quickly walk you through some examples here. So in the first example, we actually used the ASAR data, which is from the Advanced Synthetic Aperture Radar, from a satellite called the NVSat, which is from the European Space Agency. We used the time period from 2002 to 2012, and there were 23 NVSat ASAR images during that time period. And the the time period that we used was from 2005 to 2010, but the satellite was available from 2002 to 2012. The spatial resolution of this satellite was about 20 meter, and the wavelength was 5.6 centimeters. So if you remember, if the wavelength is 5.6 centimeter, the maximum deformation that you can measure is 2.8 centimeters. So hopefully you caught that. And these satellites have descending orbit and ascending orbit. In this case, we are using descending orbit images. When you do this processing, you have to use the same orbit direction. You can either use all descending images or the ascending images. Now, this is the kind of result that you would get from an INSAR analysis. Particularly in this case, we are doing a PS INSAR, which is called the Persistent Scatter Interferometric Synthetic Aperture Radar. So let me explain to you what you're seeing here. You have an area close to LA in the Palos Verdes Peninsula. That is the base map that you're seeing. And these points that you're seeing that is overlaid on the ground map is the PS INSAR values. Now, what does that mean? What does these colors mean? So let me walk you slowly through these aspects. Now, um, each of those points are just like a traditional inclinometer. And you can see here in the image I have noted down, there were over 600,000 PS points that we had from this area. This area is roughly about 10 kilometer by 6 kilometers, so a 60 square kilometer area. And in that area, we had 600,000 data points. So just imagine if you had to install 600,000 inclinometers in this kind of an area and measure the ground movements, how much it would cost and how challenging logistically it would be to implement something like that. Whereas in this case, you are actually getting those measurements of ground movements from these 600,000 points from the satellite data. And these satellite data sets are in most cases available for free. So you can actually get this data set and monitor an area for free. So this is a huge advantage compared to the traditional approach. Now, these, as I mentioned, they are individual points where you have ground movement, a historic record of ground movement, just like an inclinometer. And the colors represent the mean and the standard deviation of the where the yellow is more close to zero or there is no movement at all. The colors are represented as velocity in millimeter per year, and red means there is um, movement away from satellite. So those are areas where there is a lot of movement happening away from the satellite, which usually is kind of a slope failure or ground settlement. And green represents areas where there is uplift happening. And it could be sometimes the toe of a slope or things. Now, Here you can see there are some areas where there is a lot of settlement happening, and this is if you know the geology and the things happening in this area, there is actually some oil wells here, and these settlements are causing from the ground settling from the oil pumping in this area. Now, you can actually see some areas you don't have any information. So some areas there is no PS point. So let me quickly also give you an why that is. So there could be two reasons for that. One, it could be that there is more movement there than the INSAR could measure. So there is more rapid movement happening. So if you have more rapid movement, those areas you would not get a PS point. The second reason could be that that area is too vegetated, or vegetation often has interferes with INSAR. So those are some of the limitations that we have. If you have rapid movement happening or vegetation, you have challenges. So we can actually develop vegetation maps and other um, maps to kind of rule out what could be the reason, whether it is rapid movement or vegetation and things like that. So there is more work that can be done in that area. Now, when we were analyzing this area using the INSAR data, what we found was there was an area that was north of this called located in the Ventura County, about 100 miles northwest of Los Angeles. And there was a dam called the Casitas Dam, and it is constructed in 1956 to 1959, and it is operated by the U.S. Bureau of Reclamation. And this dam caught our attention because we actually saw that there was some movement happening at this dam location. And we started exploring more to see what is going on at this location. And what we found was we looked at some of the basic dimensions of the dam. The crest was about 2,000 feet. It was at an elevation of 585 feet. The berm height was about 130 feet. It was an earthen dam. And we also saw that in 2000, around 2000, there was a huge or costly retrofit to the Casitas Dam, which cost about 42 million. And the reason for that was there was a concern that if there was an earthquake in this area, this dam could fail and cause huge risk to the communities that are downstream of this. So they did a retrofit to stabilize the dam. Now we used the ASAR time series data for this, and we had some PS points at the dam site. So you can actually see there were some areas that are red. There are some areas which had close to zero velocity, and then some areas with blue, which is more on uplift. So the red areas were more, which is more of settlement or ground slope failures. Uplifts were more on the downside. There were some areas there were uplift going on. And we looked at this from the 2005 to 2010. And what we found was the area which we marked as 2, which has this brownish color. You can see that had the most displacement, around a total of about 40 millimeters. It displaced. You can see number 4 is this yellow color. That area was pretty stable. So this area is pretty stable. You can see that this area is pretty unstable. The 3 and 1 seems to be somewhat unstable, but not as much as 2. So we started digging more to understand what might be causing this. So we decided, okay, let's actually look at a time series of this. So we interpolated that data to see a time series. So here you can see in 2005, December 10th. How the displacement was, most of the area, the displacement was about 0 to 4 millimeter. But this area where that point two was, there was about 7 to 10 millimeter. And you can see over time where those displacements are changing. So here you would see the time changing. Now it is 2006. So we created this time series to understand what is going on in the area from 2005 to 2010. So here you can see this is 2008 now. 2009. So by 2009, there was about 29 to 32 millimeters of movement at the berm here. And you can see here, here there were about 22 millimeters, and here there was about close to 32, and somewhat in the bottom here there were further additional movements happening. So we were able to actually understand these movements started here in 2005, but it looks like it is also continuing and impacting this structure. So if you look at the area closer, when we looked in the high resolution optical images, we can clearly see that there are failures happening on the surface at here. So these millimeter scale ground movements that we detected from Insar correlated very well with what the ground is showing, because these movements are starting to express as failures on the dam. However, in the case of the berm that they constructed, although there was about 30 millimeters of movement that we saw here, we could not see any visible signs of failures. It was with the failure, the movements were not visible at this point. Now, this was a pretty significant result for us to say, to be able to detect these kind of small movements that are valuable for engineering decision making from from INSAR, and we can do this for large area. And traditionally, these measurements are done by doing one or two instrumentation. But the problem with that kind of an approach is if you had your instrumentation at one of the stable locations, so if you say, if your instrumentation was here or here, you would not have detected the problem that is going on here. Or even if you had somewhere where here, you would not have thought that this is as serious as these displacements that you would see. So in the case of the traditional approach, the location where we measure is very critical, and often it is a hit or miss by placing those in instrumentation. Whereas these remote sensing data analysis, you have a much higher spatial resolution, and that way you can actually resolve for what is happening at your site in a better manner than the traditional approach. So these were, we actually demonstrated that the INSAR has the capability to supplement long-term dam monitoring, which was traditionally done using either visual observations or by this instrumentation. Let me actually move you to another case study that we have. In this case study, we have a site from Nevada, USA. Um, this site is very close to a rail corridor, a critical rail corridor that US has transporting the material from the coast to all the way to Salt Lake City. So this is a critical corridor. Any disruption to that has a huge economic impact. So the rail company was concerned that there were some failures starting to happen along this corridor. And particularly in 2005, there was a failure, or slope movement started to show. In 2006, there was rotational slope motions observed at the site. And in 2011, there was a massive rock slide. And from 2011, the rail company started doing detailed ground monitoring and instrumentation. So the question to us was, hey, can we utilize this technology to monitor rail corridors, transportation networks, and infrastructure? And in this case, we used a different satellite also. In addition to the NVSAT, we used the ERS satellite. And the benefit of the ERS and NVSAT radar satellites is that they both have the same wavelength. And because they have the same wavelength and same sensor configurations, you can actually combine them and process it. So now you not only have the benefit of utilizing this technology and getting very high spatial resolution, but now you also have the benefit of getting historic information. So you can actually combine these two satellites and go all the way up to 1992. ERS was launched from 1992, and you can actually look at this last 2 decades on how your site was performing. And that's what we did in the case of this site in Nevada. So when we did that, we actually obtained some PS points along the slope face. And what we found was the cumulative displacement in millimeters at the slope face was close to 66 or 62, so around 60 to 64 millimeters on an average on the slope face. And if you look at the surrounding area, most of the area had very small cumulative displacement over time, 0.52 and 13.53. So much smaller compared to this one, where you had significantly higher movements happening at the face of the slope, which raised the question, why is there movement happening along here? So we looked at a time series of this, and as I said, as we combined the ERS and the NVSAT data, we had a nice time series all the way from 1992. And what we see is the slope was pretty stable all the way up to 2005. And then the slope started failing or started moving. And then by 2010, there was about 60 millimeters of movement. So till 2005, this slope was stable, no movements. Then suddenly it started moving. What is the reason? So we started digging the literature to see, was there an earthquake event happening in here, or is there anything that was going on? This actually matched very well with what the rail company had to say. They had actually mentioned that they started seeing slope movements from 2005, and rotational slope motions were observed in 2006 and so on. So their observations were were validated with the radar measurements. Now, but the question of what is going on and why this movement was happening was not very clear to the rail company or us. So while we did the literature search, what we found was there were time-stamped images from the area that there was a massive flooding that occurred in this area in 2005. So when this flooding happened and when there were derailments or the rail cars were derailed, and their tracks were destroyed, what they did was they came and immediately blasted some of the toe of these slopes to get their roadbed back and put the track back to go to have the operation. Because this was a critical line, they needed the track immediately back for the operation. And by doing that, they actually created more problem to their track. Some of the slopes have become unstable. So now the question was where all there is unstable slopes along this track that we can actually identify. So we did an analysis all along that corridor to identify areas that are vulnerable, and we were able to identify those areas for them. Some of the areas, based on our recommendation, they actually fixed it, so you can actually see some of the slopes where they have shotcreted based on our recommendation, because those areas were starting to fail and creating trouble. So here you can actually see an application where this INSAR based approach can be utilized, um, not only like for forward modeling, but you can also utilize it for a forensic study where you can actually go back and look at a historic failure and look at what might have caused, when would have it really triggered, what could be the real cause for this happening in the area. So this is quite valuable. The historic archive of radar images that is available and the spatial resolution that you can actually get from these radar images provide quite a valuable tool for geotechnical engineers to do measure the movement of infrastructure and understand the health of this infrastructure based on these movements. I want to actually point out, for those of you who are interested to work in this area, there is going to be a new radar satellite launched by NASA. This is going to be a joint mission between NASA and the Indian Space Research Organization, ISRO. The mission is called the NISAR mission. In 2023, US is going to have this mission launched, which would provide full global coverage with rapid data delivery for hazard monitoring. So we are going, this is after a long time that US is going to have a radar satellite. US has always been depending on the Canadian and the European partners for the radar data. Currently, there is the Sentinel mission from the Europe that is providing us free radar data. But this is an exciting opportunity for hazard monitoring, that US will have this, and that we will have some more opportunity to rapidly image some areas if we have hazards that are going on. So if you are interested in some research, I would encourage you to take a look at this area for if you're interested in the research in INSAR. Let me also quickly show you some examples of other technologies that can be used. So that is, one is photogrammetry. So here, traditionally, if you had to actually develop a 3D model of an area, the traditional choice of instrument was like a LiDAR. The LiDAR can be pretty costly. It's a pricey instrument. And now, with the advancements in the structure from motion, which is a technique that was developed by computer science people for more developing virtual environments for gaming and things, this is an approach that has been taken advantage by the earth scientists and engineers to develop 3D models. So you can actually use your regular DSLR camera that you have and take pictures of an area and develop high quality 3D images. So this is something that you can also utilize to monitor slopes and ground movements. In this case, you can actually see this is some work that we did in 2014 and 15 in Nevada. And let me quickly show you a video that compares the 3D models that we have developed from this method to traditional LiDAR approach. So here, what you're seeing right now is along that rail corridor in Nevada, where the slope was failing, we did photogrammetry. We took images using a drone and a DSLR camera of that area, and we can generate these high quality um, um, 3D models then we can make measurements and we can do repeat scans of the area and see whether there is movement happening at these locations or instability happening and what could be the reason for some of these. And you can see here, there is clearly a scar where the failure is happening. This is just the photogrammetry. Earlier, there was a comparison of the LiDAR also. This is just the photogrammetry. And the next one actually will show you just the LiDAR. So the photogrammetry had almost equal or better quality than the LiDAR data. So this is a huge advancement that is happening with the, so this is the LiDAR data. So you can actually get very similar quality data from the photogrammetry at much lower cost. A similar approach we did for monitoring pipelines. So this is in Alaska. In this case, instead of using an unmanned aircraft, we used a manned helicopter, and we were imaging the pipeline using a manned helicopter. And we can see we can do this over time at a pipeline location and see if there is any danger to the pipeline. For example, in this case, let me show you. Um, so over time, we did a change of ground vectors, and what we saw was the top of the slope is going down. So this is a classic rotational failure happening. So this is the slope. This area is the head of the landslide. This area is moving down, and this area is experiencing an uplift because it is the toe of the landslide. So there is a landslide developing here at this location that what we could detect from this photogrammetry. Let me also quickly show you an example of the thermal remote sensing and I'll be happy to take some questions that you have. So here, in this case, we are using thermal sensors. These are readily available sensors from FLIR. There are several versions of this. In this case, we used FLIR View Pro and FLIR Tau 2. There are more recent uh, FLIR versions like FLIR Duo Pro, which can actually allow you to collect both the thermal and optical data. And the benefit of this kind of approach is you can understand how the structure is responding to change in the temperature. So in this case, what we are looking at is a bridge, and we are actually looking how the bridge is heating over time. So we image that area 2 times. We image it early in the morning before it is warm, and then we image it by around 11 p.m. or sorry, 11 a.m. when there is some heating of the bridge happened. And what we calculate is we estimate the change in temperature. And this change in temperature is a function of the density of the material and the material characteristics, the subsurface characteristics, how the material would heat up. So in this case, we can actually see in the bridge, there were areas that were heating up faster and areas that were slowly heating up. And what we found was these areas that are heating up faster are areas where there is delamination happening. And this is basically the concrete is peeling off and creating air pockets and underneath. And because of those air pockets, there is heat being trapped at the top. So you have higher heating. So you can actually utilize this technology to monitor the concrete dams, the stability of the dams, how the concrete is performing. So traditionally, remote sensing techniques were limited to the surface, but we find that by utilizing some of these technologies like the thermal remote sensing, you can actually start not only observe things at the surface, but also at the subsurface and look at defects that are going on. So to summarize, with Insar, there is a rich data archive for forensic investigation. Millimeter scale movements can be observed from satellite platform using stacking techniques, and they provide opportunity to proactively monitor infrastructure because now you can actually scan large areas, identify areas that are vulnerable, and if you need to strategize your data collection, you can actually plan where you need to do some more in situ measurements. They provide improved spatial and temporal resolution, and the thermal remote sensing is uh, valuable for monitoring integrity of concrete structures, bridges, retaining walls, dams. I've not shown you, but we have examples where we can actually utilize the thermal signatures to identify internal leaks that are happening in dams where there's moisture seeping and things like that. Photogrammetry, the user has more control on the temporal resolution because that's something that you can easily collect using a drone. It's a cost effective and provides centimeter scale accuracy to monitor ground movements. And its simple processing makes it an attractive approach for many infrastructure monitoring applications. So these are some, this is a summary of this, the INSAR thermal and photogrammetry, how it is being utilized for geotechnical engineering and performance monitoring. I want to actually acknowledge the contribution of my postdocs, graduate students, collaborators, and all the funding agencies that have helped to um, get make this work happen. Without their support and the work, and none of this would have been possible. So I want to acknowledge their support, and happy to take any questions that the group has here.
Excellent. Thank you. Thank you very much. That was really cool. I'll have some questions, but I'll let other people go first because mine are very general and I am not an expert. So I would
Okay, no
expect
problem.
Ninad, yes, to have a question.
Hello, Dr. Oommen.
Hello, Ninad.
Was a
I think you're
very
breaking.
good lecture. My question is, when you said that whatever wavelength the sensor has, we can measure half of the amount of the deformation, right? So if we have 5.6 centimeter, we can measure up to 2.8 centimeters. But when we do this kind of analysis on active volcanoes or volcanic eruptions, usually in the publication we see that they mention that we have 600 millimeters, so 60 centimeters subsidence or uplift or something like that. So how can in case of volcanoes we measure up to 60 centimeter, but in case of residential areas we measure up to 2.8 centimeters?
Good question, Ninad. So let me actually clarify. So what I mentioned by the half the wavelength that you can measure is between two acquisitions, you can only measure half the wavelength. But over time, you can actually measure 60 centimeter or 60 millimeters. So if you have a time series, for example, some of the images that I showed, we were measuring up to 60 millimeters. That's because we did have a time series over time. So cumulative you can actually do, but between two images, you can only do half the wavelength, be it volcano or any place, the same, because it's the same technology that we are using. Hope that is clear.
Okay, thank you, sir.
Okay. Any other questions?
Xiaobing, I think looks like you're unmuted. Do you have a question?
Yes, this is Xiaobing, geophysics faculty. Thank you, Tom. Very good talks.
Thank you.
I have one question about the correction of the INSAR data impact due to the moisture. And there are a couple of publications about the phase angle caused by the moisture. How do you think about that?
Yes, we do need to do some corrections for moisture when we are working in coastal areas. But what we have found is that when we actually stack the images and process over a long time period, we can actually correct for these corrections from the moisture, because over a long time period, you would not have those effects consistently in the image. So we look for areas which can have consistent signal over time, and then we filter those areas and take only those points for our analysis. And that's how we have actually accomplished this. So the PS Insar approach helps us to overcome. So if you do individual interferometry between two images, then you have the challenge of the moisture corrections that you need to apply and understanding those atmospheric parameters for that. But if you take for over a long time and then look for consistent peaks, scatterers, which is called the permanent scatterers or persistent scatterers, then you can actually identify points where there were no interference.
Okay, thank you.
Anybody else have questions? I have a couple of very basic general ones. If anybody else has any other questions. Okay, I'll start with mine then. So traditionally, how many sensors would the people in charge of the dam, put on a dam, and how much would that cost them to keep track of the dam?
Yeah, so traditionally, in some cases, it depends upon the project, which agency has the dam and things like that. Some of the bigger federal government dams, they have multiple sensors, but some of the smaller dams, for example, two dams that failed in Michigan last year, in Midland, Michigan, they did not have any sensors. So some of the private dams, there is no sensors. So there is a big variation of the number of sensors that. Now, in terms of the cost, some of these sensors, they are not very costly. They are probably they're within like 2,000 to 5,000 range, but the installation and the maintenance of these sensors are more expensive because you need to check whether these installations are working over time, whether there is any failure, these data collection. So that can be quite a bit of a challenge, more than just the installation itself. I'm not saying that installation is easy, because these are installations that you have to do to the subsurface. So you have to drill and do this installation. But those are at least one-time costs, but over time, the maintenance cost of this becomes challenging. And what we find is just 1 or 2 points, often we don't have the resolution to understand what is going on at the site. And you can be lucky, you might get at the location where the most movement is happening, or you could be on a very stable location and not ever detect what is going on at that site.
Okay, cool. My other question is, so all of the photo mosaics, what program, so you can just take those images, and then is there a particular program that you use to map them on the topography? And that's
Yes.
easy to do.
Yes, actually, there are a couple programs that can be used. There is one called Agisoft, and there is another one called Pix4D. The Pix4D is one that is commonly used now to do this kind of approaches. Very, very easy to process. It has a lot of application, not just in this earth science or just for slopes, but you can actually develop any other models, even any 3D models that you want to develop. You can actually take these images and put it in these softwares and get very high precision 3D model. So Pix4D would be the software to look for if you are interested in utilizing that.
At least we do have a Pix4D.
Oh,
We do on
Yes.
campus. Cool. Yeah, those images were really cool with the pictures and the satellite data in the same one, and then it's just the pictures themselves. Cool. Yeah.
Excellent. Yeah,
If you use, just let me know.
Oh, okay. Thank you, Xiaoming. I guess I need a drone. Does anybody have one of those? Yeah, no, you guys do. Cool. Yeah.
There is a lot of opportunity in that drone sensing research because traditionally we had the satellite-based remote sensing observations, and we were able to make regional scale assessments. And the problem when it came to engineering was that we did not have the resolution to make decisions and design based on these remote sensing observations. They were too cores for the engineering decision making. But with the advancements in drone imaging and sensing, now we are able to get much finer spatial resolution data that can be utilized for engineering decision making. And not only for the spatial resolution, but we also have now control on the temporal resolution. We can actually collect at any time. We can collect it below the cloud, so we don't have some of those issues that we had with the traditional satellite imaging in terms of data collection. So it's a powerful area.
Thank you. Yeah, I really enjoyed that. That was really cool. Does anybody else have any questions for our speaker today?
Tom, that's one question curious. Do you
Yes.
know any Insar possibility that we could use for drone? I did not see anything of that, but I think probably a lot of people looking forward to that.
Sorry, I missed that. It was breaking for me.
The Insar capacity put on a drone.
The Insar capacity put on the drone.
Yeah, just like a drone-based Insar.
Yeah.
Do you know anything about that?
So one of the challenges with that is we need to have very precise orbit to be able to image with the radar to have the phase change measured. So, and we don't have that kind of a precision on the drone platform right now to be able to precisely send it from one area to the other. We are getting there, but with the wind and everything, our drone imaging is not that precise in terms of the location on the space on the air. And that is going to be very critical. There was a project where rail companies were interested to look at that technology, and we had actually looked at whether we can actually put a radar synthetic aperture radar sensor on a rail platform and image the corridor. In the rail, you can actually do because you have the same repeat pass from the railway, so you have that precise location. But there are some other challenges that we were facing from the rail. But from the drone, it's still in its early stages. I know there are a few people trying to do that. There is some work done at UMass Lowell. There is a professor there trying to do Insar from a drone platform, but there is a little, I think we are still, it's not quite resolved.
Okay, thank you.
Yeah. But something that would be a very interesting area to work in. If it's a challenging problem, but
Yeah, that's what I was looking for.
yeah.
Excellent. Any other questions for our speaker? Okay, well, thank you. I know we didn't exactly clap over Zoom. It's always hard. Thank you so much for taking the time to present to us. Oh, Ninad's clapping virtually. And yeah, we really appreciate it. And that was very interesting. So
Hey, thanks for having me. And yeah, if you have any questions on any of these topics that I discussed, please feel free to
hey,
write to me.
sounds good.
Happy to interact.
And we'll be discussing your seminar in the seminar class, on Friday. So
Okay,
I'll
perfect.
send students your way if they have questions.
Absolutely. No worries.
Excellent. Thank you very much.
Okay. Take care. Bye.
Bye.